So we're going to talk about the first derivative test, which finds where functions are increasing and decreasing. The first part of your notes is a lot of fill in the blanks, and it's based on the graph. Instead of kind of scrolling back and forth, I'm going to stay focused on the graph and read the blank so you know what to fill in. But that way we can still reference the graph, so I don't have to scroll back and forth. It says determining intervals on which a function is increasing or decreasing. Derivatives can be used to classify relative extrema as either a max or a min. Okay, so we have found these extrema, but we're going to use derivatives to figure out if they are maxes or mins. As we begin to focus on analyzing functions, we can determine some predictable and specific behaviors for functions in our calculus journey through the mathematics of change. So example 1, this exploration leads to conditions and outcomes for the first derivative test. Use the graph of the function f to answer the questions below. Okay, it says use a red color pen. Okay, so let me get my red. All right. Local max of f do not include the endpoints. Okay, so state the x values where a local max of f occurs. State the x values where a local max occurs. And that would be here and here. Okay, so those x values would be a and d. So I would write x equals a and x equals d. Okay, at each max value, f changes from, okay, so at both of these max values, the original function is changing from increasing to decreasing, because it's increasing into the max and then it's decreasing coming out. Increasing into the max, decreasing coming out. So changing from increasing to decreasing. Okay, so now what does that mean in terms of the derivative? Well, if f is increasing, then f prime is positive, because the slope here would be positive and the slope here would be negative. So if the derivative changes from positive to negative, then I know that's a max. So what's going to happen, so a little foreshadowing is, I'm going to give you a graph of f prime, and I'm going to ask where a max of f occurs. And that's where f prime changes from positive, above sea level, to negative, below sea level. Okay, now it says use a blue colored pencil, circle all the points to min. All right, so here's where I'm going to kind of stop scrolling back and forth. So min looks to be here. So that happens at x equals c. At each min, f changes from decreasing to increasing. So I'm going to let you fill that in. F is changing from decreasing to increasing. And the next one should be about its derivative. Yep. So the derivative is going to go from negative to positive. I don't know why I put a 1 there. That should just be a negative to positive. From negative to positive. Okay, at each relative or local extreme value, f prime, the derivative is either blank or blank. So the derivative at these places is either 0 or undefined. Or you can put the D in E, either way. Okay, now it makes really easy sense going from the original function to the derivative. Where it gets tricky, just again foreshadowing, is when I give you derivative information and ask you about the mother function. So that's kind of where we need to slow down and make sure that we see the connections. Okay, using a green colored pencil, sketch the tangent line, if possible, at the following points and determine their signs. Okay, and again, I'm going to stay on the graph, but I'm going to read this section right here, and I'm just going to let you fill it in as we go. Okay, so I'm going to erase what we have so far, and I don't have green, I have purple. Okay, so it wants the tangent line at point B. So here would be B, so the tangent line would do something like that if I could draw well. So f prime of B would be negative. That's a negative slope. Describe the change in the behavior of the graph f at this value. Okay, I'm going to erase my line and just look at the point. Well, it's decreasing, and it's decreasing going into the point, and it's decreasing coming out of the point. So that can't be what it's asking for. So look a little deeper. It's changing from concave down to concave up. Right there. So describe the change in the behavior of the graph of f at this value. So I would say it's going from concave down to concave up. Okay. And then point D wants the tangent line, which I can't draw. So f prime of D is undefined. Describe the change in the behavior. Well, it's not about concavity because I'm concave up on the left and I'm concave up on the right. But it does change from a positive slope to a negative slope. Describe the change in the behavior of f. Yeah, f goes from, oh, well, that's, sorry, I can't say positive slope, negative slope because that's f prime. F goes from increasing to decreasing. So for part B, the change in the behavior of f goes from increasing to decreasing. At the point E, so E is where it kind of flattens out, so its tangent line would kind of do that. So f prime of E is going to be 0. Describe the change. Well, it's decreasing the whole way. So this is a concavity issue. It changes from concave up to concave down. Think about contact lenses. So this is your lens. If it's sitting on your finger and you're about to put it in your eyeball, it's sitting up, concave up. And this is concave down, like if you were to lay it down on the counter and it would kind of bubble up a little bit. Concave up and concave down. Of these 3 points, which two are points of inflection? Okay, so inflection is a new word, I think. Yeah, it's a new word for y'all. Inflection is where the concavity changes. And that's going to be a word that we use tons, especially on the second derivative test, which is coming next week. But for right now, let's just kind of introduce that word. Of these 3 points, which 2 points are inflection? And that's going to be where your concavity changes. So that's going to be x equals b and x equals e. If a function f has a relative extremum at a point, then the derivative at this point is either 0 or undefined. That's a true statement. Is the converse of this statement also true? So if I have the derivative that is 0 or undefined, does that mean that it's an extrema point? No, look at point E. E has a derivative whose slope is 0, and it's not an extreme point. Oh, what points justify your answer? Well, there you go. And I'll write this one out for you guys so you can see it. But I hope everybody see that, like at E, that's where the derivative equals 0, but that is not an extreme point. Like that's not a max or a min. That's just kind of along the way. So what we would say for him, no, at x equals E, f prime of x equals 0, but no extrema at x equals E. Okay, so all that is just to kind of start the ball rolling about increasing and decreasing and f prime being positive or negative and some concavity changing. So the ball is officially rolling. Here we go. Definitions, increasing and decreasing functions. A function f is increasing for any two numbers, two x's, on the interval. If one x is smaller than the other, implies that the y is smaller than the other y, because that's going to make it go up, increase. And then the complement to that statement is if x1 is bigger than x2, then that y that goes with that first x is bigger than that second x. Please don't get hung up on this. You're never going to have to state that. It's just sort of, I don't know, putting a definition where there didn't really need to be a definition. But there it is for increasing and decreasing. The graph of y equals f of x is shown at the right is defined on the closed interval -3 to 7. List the open intervals on which the function is increasing, decreasing, or constant. I don't know if you remember this from pre-cal, but I said if it's increasing, decreasing, or constant, nobody gets to claim that endpoint or that transition point. So it all goes with parentheses. So we are increasing here. So from -3 to -1, then we are constant from -1 to 2, and then we are decreasing from 2 to, what do we go, 7? There we go. Note, a function is said to be monotonic on an interval if its first derivative, which need not be continuous, does not change sign. Okay, that's awesome. Moving on. How can we find the values of x on the graph of a function where it is increasing, decreasing, or constant? Some important ideas come to mind here. If f is continuous, then the derivative can only change signs at a critical value. And if f is discontinuous, then the derivative should change signs at a critical value or at a discontinuity. So that would be where your derivative does not exist. How to find intervals of increasing and decreasing. Now, make sure that we're clear here. We're finding intervals of increasing and decreasing, not maxes and mins. Because if I'm discontinuous, like if I have an open circle or an asymptote, that's not a max or a min. But it does end an interval of being increasing or decreasing. So let f be a continuous function on the closed interval a to b. Find the intervals on which f is increasing or decreasing. Now, step number 1, find the critical values, including discontinuities, on the interval a to b. Number 2, create a number line chart using these critical numbers. Choose x values in between the critical values to test the sign of f prime on your sign chart. Note, your sign chart is not a valid justification. You must write a clear and concise statement communicating your mathematical language related to the sign changes of the derivative. Do not use pronouns. So you cannot say it. You have to say f or f prime. That's like if I said my dad and my brother went to the store. He got a bag of ice. Well, who is he? Is he my dad or is he my brother? So don't use he's. Don't use it. Call them by name, f or f prime, and then later f double prime. For example, the function g is increasing on the interval -2 to 5 since g prime is greater than 0. And I would say you could probably get away without doing this and just saying g of x is increasing on the interval since g prime of x is greater than 0. Now we're going to do this number line chart because that's sort of the muscle behind that statement, but you have to have the statement. Okay, and we're going to practice this. All right, here we go. Determine the intervals on which a function is increasing or decreasing. Find the open intervals on which that, which is a cubic, super well-behaved function, always continuous, is increasing or decreasing, and justify. Now, no skimping on these steps. This will be on an FRQ. I would almost guarantee it. Almost. So that's a high probability. Okay, so we are looking to gobble up like hungry hippos. We're gobbling up all the points we can get. So we don't want to skimp anything just because we know what something implies. We have to communicate it. Okay, so we have to do it in the way that what they're looking for. Okay, so step number 1 is I'm going to find my derivative. Okay, so 2x squared minus 2x minus 4. Okay, then I'm going to take that derivative and I'm going to set it equal to 0 because I'm trying to find my critical values. This I do not have to worry about because that's a very well-behaved function, the cubic and the quadratic, so I don't have to worry about the derivative ever not existing. That's a cute little quadratic function. To find this part, I'm going to GCF a 2 out because it makes life easier, and I'm all about life being easier when it can be. And feel free to pause and digest or work something out. I'm cruising through this because I know that you can pause it at any time. Okay, so now that I have my critical values, I'm going to find my sign chart. Now my sign chart is going to put my 2 critical values on the line. Okay, so what I'm going to do is I'm going to label. On top, I'm going to find f prime, and on the bottom, I'm going to say what that means f is doing. So what I'm going to do is I'm going to pick a number that's somewhere less than -1. Now, I don't really want to plug in like a -10, so I'm going to plug in a -2. So I'm going to try a -2. I'm not going to mark it and put a -2 because I don't want I don't want to think that -2 is a critical value. So it's not. Now, if you want to just put a little -2 right there, in between -1 and 2, I'm going to try 0 because it's 0. And over here, I'm going to try 3. Again, I'm not putting a tick mark because I don't want to confuse it for a critical value. Okay, so I'm going to take a -2 and I'm going to plug it into f prime. Now, let's be clear about our mission here. I'm not looking for the number value. I'm not looking for the numerical value. I'm looking to see if this thing is positive or negative. So here's a nice little hint. Don't take your -2 and go here. Take your -2 and go here. Now, I should have brought that 2 down. Go here. Because all I'm interested in is the sign. Well, that's going to be positive. So positive. If I plug a -2 in here, that's going to be negative. So times a negative. And if I plug a -2 in here, that's going to be a negative. So what's a positive times a negative times a negative? That's a positive. And guys, that's exactly what I do right there. Like I have my 3 little signs that represent the 3 little dudes down here once I have factored them. And then I multiply them all together. And again, I don't care what the number is. I care about the sign of the number. Okay, so now I'm going to plug in a 0. So again, I've got my 2. He's positive. I'll plug a 0 into the middle one. 0 minus 2, that's a negative. And 0 plus 1 is a positive. Positive times a negative times positive is a negative. Okay, now I'm plugging in a 3. Well, that's going to be a positive 2. Plug in a 3, that's going to be positive. And that one's going to be positive. So he turns out to be positive. So now I know that f prime is positive less than -1 and greater than 2, and negative in between the two. So what does that mean for f in terms of increasing and decreasing? I know that that means that f is increasing, and then here it's decreasing, and then here it's increasing. Now some people don't like the arrows and they like to do increasing, decreasing, increasing. Some people love the arrows and some people do both. So it is whatever floats your boat, because again, the grader is not using what we see right here as your end all be all. It is part of the problem. It is part that's going to get graded, but it's your conclusion that matters the most. So my conclusion is, now remember, no pronouns, so I have to call them by name. F of x increases, or you could say is increasing, however you want to do that, on negative infinity to -1 and 2 to infinity. But now you have to say why. Because f prime of x is greater than 0. Then I'm going to come in here and I'm going to say f of x decreases on -1 to 2 because f prime of x is negative or less than 0. That is a beautiful problem. I've got my work, I've got my thinking, and then I've got my conclusion. Gorgeous, gorgeous, gorgeous. When presented with a continuous function, knowing that the sign of the derivative changes at a point, as well as knowing how the sign changes, gives us insight into the extrema. So now, let's talk about the formal first derivative test. Let C be a critical number of a function f that is continuous on an open interval. If f is differentiable on the interval except possibly at c, f of c can be classified as follows. F prime of c changes from negative to positive, then f of c is a minimum. If f prime changes from a positive to a negative, then it's a max. If it doesn't change, then it's neither. Okay, pause and come back here. Hold on. Look at this red stuff over here on my sign chart. It increases and then it decreases. So tell me about f at -1. It has a max. I don't know what the max is, but I know at -1 it has a max. If I wanted to know what that max was, I would plug a -1 into the mother function and I would get its y value. Okay, now this decreases and then increases. So what happens to f at 2? Well, that's a min. No. I'm so sorry, I said that wrong. That is not a min. That is where a min happens. A minimum happens at x equals 2. To find out what the min is, I would plug a 2 into the mother function and get his y value, and that would be the min. Okay, so once I've used my f prime to figure out where everything is positive, negative, I've transferred that into, or interpreted that into what it meant for f, increasing and decreasing. Now I can use the increasing and decreasing, if it changes, to determine that that is where a max or a min occurs. That's what all of that is saying. All right. Now this right here, I have a copy for you and am giving them to you as I see you in class. So whoever was in class yesterday got one, and then as I see you guys next week, I'll give them to you. But this is a very handy dandy chart. If you are Plan C, then I would pause this and write that down on like a note card or something, because that comes in super, super, super handy. Okay, here's what we know so far. I know that if f prime is positive, that f is increasing. I also know that if f prime is negative, f is decreasing. That's it. That's all we know so far. Okay? The other stuff will come, but not until later. So right now, everything that's in yellow, we have just gone over. Okay? Given the function, oh yay, it's just a cute little degree 4, it's super continuous, super well behaved. Find the open intervals on which f of x is increasing or decreasing, justify. Determine the x values for any local extrema of f of x, justify. Here's what I'd love you to do. I'd love for you to pause it, and I'd love you to take a whack at this one. Okay, if you get stuck, then hit play and get me up to where you are, get unstuck, and then pause me, and then keep going. Okay, but see how much of this one you can do on your own, pretending it is an FRQ, and that APIs are going to be on your paper. All right, so I'm going to start with finding the derivative. And then I'm going to set that equal to 0. I'm not overlooking this part, but it just doesn't ever happen. And you don't have to acknowledge that, but just know that sometimes there are functions where the derivative doesn't exist, and that is going to contribute to your critical values. So just, you know, it's there. I'm just sort of acknowledging the elephant in the room. Okay. And then to solve this, I'm going to GCF. And I'm going to get a 0 and a plus or minus 2. But you know what? I know it's coming, and I want to factor this because of that wonderful number line. Okay. I want the 3 pieces because it makes it easier for me to do my chart. Can be done with the line above it. It's fine, but just for my little brain, it just makes it easier. Okay, so I have that. So now I'm going to do my line. And f prime goes up there, and f goes there. And let's see, I have a -2, a 0, and a 2. Okay, so I'm going to pick a -3, a -1, a 1, and a 3. Okay, so if I plug a -3 in there, he's going to be negative. -3 in there, he's going to be negative. And a -3 in there, he's going to be negative. So that puppy's going to be negative. Now I'm going to plug in a -1. He's negative. He's positive. He's negative. Negative, positive, negative. That's positive. Plug in a 1. Positive, positive, negative. That's negative. Plug in a 3. Positive, positive, positive. That's positive. Okay, so for f, that means decreasing, increasing, decreasing, increasing, and it's a degree 4. Like I knew this was going to happen. It looks like a W. So here, what did it want? Find the open intervals on which we're increasing or decreasing. Okay, so here's the fun part. F of x is increasing on the open intervals from -2 to 0 and 2 to infinity because f prime of x, what are we doing? We're increasing, is greater than 0. F of x is decreasing from -infinity to -2 and from 0 to 2 because f prime of x is negative. Okay, so that's part A. And all the purple and the red and the blue is all my justification. Okay? Determine the x values of any local extreme of f of x. Okay. Now, don't read what you want to read, like read what is there. Determine the x values of any local extreme of f of x. It's not asking for the y values. It's saying where does the local extrema happen? Okay. Well, let's see. Local max occurs at x equals 0 since f prime changes from positive to negative here. Local min occurs at x equals -2 and 2 since f prime of x changes from, okay, now we're a min, so min's going to change from negative to positive here. And I know it's like, oh my gosh, like this is so Captain Obvious. Why do we have to write this out? Well, you know, you want the points, you write it out. You want to miss points on something that's super easy? Don't worry about writing it out. And there are no shortcuts here. This is what you have to have. No shortcuts. No, there's not an easier way to do this. No, there's not a shorter way to do this. This is what it has to look like. Okay. Find and justify any exact values of relative extrema. Okay, so got a little bit more interesting functions going on here. Like everything before now has been very well behaved. But for A, we now have a sharp turn because it's an absolute value. You are expected to know what he looks like without a graphing calculator. I know that he's going to go left 2, up 3, and open down. So I know he has a sharp turn at x equals -2. So, I mean, I could sit right here and answer the question. I know that he's got a max at x equals -2. Like, done. But I got to show the stuff if I want the points. Okay, so I don't have any of that. Does not exist. There is no place on that graph where the derivative is going to equal 0. That's not. The derivative is positive, and then the derivative is negative, and here the derivative does not exist. So now we're living over there. The derivative does not exist at x equals -2. So there's no like f prime to go find. Like I know that x equals -2 is a critical value. So he is going on my number line. Like it almost makes it easier, makes it less work. So let's see, this is, let's see, he's f prime and he's going to be f. I know from looking at my graph that f prime here is going to be positive because it's headed up. Now, if you wanted to algebraically think about this, let's take a -3. Well, but I don't have a derivative to plug them back into, so no, let's not. And then I know that the slope of my line is headed down, so I know that my derivative is negative over there. I know that means that f is going to be increasing, and then here it's going to be decreasing. So now I'm ready to write my conclusion. It wanted relative extrema. Relative, and that would be a max. Relative max at x equals -2. Since f prime of x changes from positive to negative. I have a relative max at x equals -2 since the derivative changes from positive to negative. I never found the derivative. Don't have to. I'm using all of my tools in my toolbox, all of my knowledge. I know what that graph looks like. So I know his derivative is positive headed up towards the -2 and negative headed south, or headed away from the -2, to the right of the -2. Okay. All right, for B, B has issues. The original function has an asymptote at x equals 0. So that's a huge red flag. Like that's a point of importance, because well, first of all, relative extrema can't happen at an asymptote. Think about what happens at an asymptote. Even if they both go up, like let's say I have an asymptote here, even if they both go up, that's not a max, that goes up forever. And if one goes up and one goes down, then that's definitely not a max or a min. So maxes and mins will not occur at an asymptote. But I still have to acknowledge him. He's still going to end up on my number line. Okay, now this is something I can take the derivative of. So y prime equals 3 minus x to the -2, which is 3 minus 1 over x squared. I'm going to set that equal to 0. I can get some solutions out of this. So I can do this, and I can do this. I can do both of them. This one I'm doing right here. This one, well, look at it. Where does the derivative not exist? Well, I can't, the denominator cannot be 0. So does not exist is at x equals 0. So both of these kind of jihad together. All right. So to solve this one, I'm going to subtract 3 and divide by -1. So that gives me 1 over x squared equals +3. Then I'm going to multiply both sides by x squared. Then I'm going to divide by 3. And then I'm going to root both sides. Square root of 1 is 1. Okay, so it looks like I have 3 points of interest. I have -1 over √3, a 0, and a +1 over √3. So I need to know f prime, and then I need to think about what that does to f. So -1 over √3. I don't know. Let's try, I don't know what that decimal is. √3 is going to be, let's see, √4 would be a 2. So √3 would be less than that. So that's going to be less than a -1/2. I don't know. I'm just going to go like super negative. Like let's go -3. Then here, let's go like really close to 0. Let's go like -0.1. Then we'll go +0.1, and then we'll go +3. All right, so if I, where's my derivative? Here he is. If I plug in a -3, okay, plug in a -3 into the bottom square, that'd be a +9. 3 minus a 9th would be positive. Okay, so that means he's increasing. A -1/10. So a -1/10 squared would be like 1/100th. 1 over 1/100th would be 100. So 3 minus 100 is massively negative. Okay, so let me show you what I just did. 3 minus 1 over -0.1 squared. So that would be 3. This is a 10th. So think of it like this. So that would be 1 over 100. Well, if you Bojangles that, that would be that, which would be massively negative. Okay? They expect you to be able to handle stuff like that without a calculator on the non-calculator section. Okay? So massively negative, which means I used a pronoun, which means F is decreasing. Okay, now I'm going to try +0.1, which is still going to give me like, I mean, all that does is change that. So none of the rest of it changes because it gets squared. So still negative. which makes sense that it didn't change at the asymptote, because remember we said that you can't have a max or a min at the asymptote. So it makes sense that I'm negative on both sides. So decreasing. And then at a positive 3, well, plugging in a positive 3 and a negative 3 is going to give me the same thing because it's getting squared. So he's going to be positive, so increasing. Okay, so let's see. Find exact values of relative extrema. Oh, you know what we didn't do? We didn't find the actual extrema. We just said relative max, but it wanted us to find the exact values of the relative extrema. So it's at, I'm sorry, let's backtrack. It's at x equals -2. So I need to find f of -2. I'm so sorry. So that would be 3 minus -2. That'd be 0. So 3. Relative max of 3 at x equals -2. Okay. Because now we got to do this, and this is hideous. All right. So I'm going to plug in, a -1 over root 3 into that original function. Oh, gracious. 3 times -1 over root 3 plus, all right, 1 over with just Bojangles. There we go. So -3 root 3 minus root 3. Yeah, that looks good. I'm going to leave it just like that. And then I'm going to plug in a positive. So 3 times 1 over root 3 plus 1 over root 3, which would be root 3. Okay. So this one is the relative max. Max of this at x equals -1 over root 3. Oh, I have to have my y. Because f prime changes from positive to negative. Whew, almost lost that one. All right. This is a min of that at x equals +1 over root 3 because f prime changes from negative to positive. That is hideous, yet kind of pretty. I know, it's hideous. It is, but it's kind of pretty. It has some really good crunchy algebra in there. I mean, that's a great problem. So let's acknowledge the fact that I put the 0 on the number line because it was an asymptote. It is where the derivative does not exist. It is a point of discontinuity. So I'll put it on there, but I am expecting the derivative to not change signs on either side of 0. And it didn't. It was negative on the left-hand side and it was negative on the right-hand side. So just expect that to happen when you're doing these. Okay. All right, number 6. Find the exact values of any relative extrema. Oh, yay, trig. On the interval 0 to 2 pi. All right. Tell you what, pause me and just try. See how far you can go until you get stuck. Okay, so the first thing I'm going to do is find my derivative. Sine's very well behaved. 1/2 x is very well behaved, so I don't have any, does not exist here. Derivative, there we go. If I set that equal to 0, I'm going to add the cosine over. So where is cosine 1/2? And I have to stay in my interval 0 to 2 pi, which is just a lap around the circle. Cosine 1/2. So cosine positive, pretty ugly. Pretty ugly is the tall one. Quadrant 1 and 4. 5 pi over 3. And yes, expected to know this without a calculator and without a unit circle. Yep, that's why I beat you on the head with it in pre-cal. All right, so I have a pi over 3 and a 5 pi over 3, f prime, and what it does for f. Okay, so, oh, and I can't go outside of 0 and 2 pi. So I'm kind of, my number line is kind of bounded by 0 and 2 pi. So pi over 3, think of the unit circle less than pi over 3. I'm going to go pi over 4. And in between pi over 3 and 5 pi over 3, like that's from here to here. Well, I'm going to choose pi because that's a nice round number. And then from 5 pi over 3 to 2 pi over 3, that's that piece right there. What's the pi over 4 over there? 1, 2, 3, 4, 5, 7. 7 pi over 4. There we go. I just like the 45s. Okay, so here I go. I'm going into the derivative. So 1/2 minus cosine of pi over 4. That's root 2 over 2. All right, square root of 1 is 1. So the square root of 2 has got to be greater than 1. Bottoms are the same. That top is bigger than that top, so that's going to be negative. Let's go ahead and do the 7 pi over 4. 1/2 minus cosine of 7 pi over 4 is also going to be root 2 over 2. So he's going to be negative. Pi cosine is a negative 1. So 1/2 minus a negative 1, definitely positive. Okay, therefore, his name is G. G of x has a relative, yeah, looking for relative extrema, a relative, let's see, oh, I didn't do my decreasing, increasing, decreasing. So this would be a min, relative min of, okay, now I got to find what it is. Happens at pi over 3. So I need to go original function, and I need to find g of pi over 3. So 1/2 times pi over 3 minus sine of pi over 3. Hold on. Yeah. Okay, sorry. Sine of pi over 3. Sine, pretty ugly. Ugly. Root 3 over 2. So pi over 6 minus root 3 over 2. Pi over 6 minus root 3 over 2 at x equals pi over 3 and then y, because f prime changes from negative to positive here. Okay, erase my chicken scratch. G of x has relative max of, okay, I gotta go find the max, 5 pi over 3 into the original function. G of 5 pi over 3, 1/2 times 5 pi over 3 minus sine 5 pi over 3 is down there. Sine, pretty ugly. Negative ugly. So 5 pi over 6 plus root 3 over 2 at x equals 5 pi over 3, because f prime of x changes from positive to negative here. I think the BC for because is fine for your homework and it's fine for me. I don't know if I would lay that card down on an AP exam. The last thing you want is for someone to think that texting has made the English language go to pot and these kids don't know how to write and that kind of thing. So I would write out the word because. But for me, I'm totally cool with BC. That totally gets the point across. All right, super awesome. Make sure you answer the question being asked. Are you looking for the extrema, which are the y values, which is what it wanted here, or are you looking for where the extrema occurs, which is the x value? And good practice, anytime they ask for the extrema, tell them what the extrema is and tell them where it happened, because you have to have the where it happened to get the what it is. So you already have that information. Go ahead and give that to him or to them. Before, I think a page ago, they only asked for where it was. So we didn't have to find what it was. We just had to tell them where it happened. Okay, last three. Oh, yay, it's a 2/3. That's a cusp. It's going to have a cusp. All right, he is going to have a cusp where the derivative does not exist. So just have that on your radar. All right, here's what I want you to do. I want you to pause me, and I want you to go find the derivative, and I want you to find the places where the derivative equals 0, and I want you to find the places where the derivative does not exist, and then I want you to hit play. Okay? All right, so derivative. There we go. Yep. Okay, so there's my derivative. So I'm going to set the derivative equal to 0, and I need to figure out where the derivative does not exist. Derivative equal to 0 is easy because the bottom is going to go away. When you multiply both sides by the bottom, the 0 eats it. I have 4x equals 0, which means x equals 0, and that's one of my critical values. Okay? Does not exist. Now go back and look at the original derivative. I'm going to look at this guy because I've already moved it into the bottom. So it's where, for this one in particular, it has a denominator. Denominator cannot equal 0. So x cannot be a plus or minus 2. So that's where the derivative does not exist. So those are my critical values. So here I go. I'm going to change colors. All right. I've got a -2, a 0, and a 2. F prime and F. Okay. So now pause it. Take numbers in each gap. Plug it into the derivative. I'd probably go into the one that has the arrow on it. And although it doesn't matter, and figure out the positive and negativeness of f prime, draw your conclusion about f, and then if you feel comfortable, go ahead and start your conclusion. You are finding the relative extrema, which means you do want the max and min values, not just where it happens. Okay, so pause, unpause me if you get stuck. So I am going to pick, let's see, a -3, a -1, a 1, and a 3. So if I plug a -3 in, on the top, that's going to give me a negative. On the bottom, -3 squared is going to be a 9. 9 minus 4 is 5. It's positive from there out. So a negative over a positive is a negative. Again, I'm not interested in numerical values. I'm interested in the sign of the answer. So I'm plugging a -1. That's going to be negative on top. A -1 on the bottom. -1 squared is a +1 minus 4 is negative. And then I'm going to cube root it. That's going to stay negative times the 3. That's going to stay negative. That makes that a positive. Plug in a 1. Positive on top. 1 squared is 1 minus 4 is negative. It's negative from there out. Negative. Plug in a 3. 3 squared is 9 minus 4 is 5. It's going to be positive on the bottom and positive on the top. And if I'm doing that too fast and you can't see where that's coming from, then you pause it and you plug these numbers in so you can see it. I'm doing it in my head. Negative, increasing, decreasing, increasing. Okay, so again, please notice that we do have maxes and mins happening where the derivative does not exist because it's not a discontinuity, it's a cusp. Okay, for the original function. All right, so I'm going to say, here's my conclusion. F, no pronouns. F, so you would never say it has a max. You would say f of x has, and they called it relative extrema. So relative min of, now I need to go find it, but it happens at x equals -2 because f prime of x changes from negative to positive. F of x has relative max of, need to go find it, at x equals 2 because f prime of x changes from min. Changes from negative to positive. Oh, changes from positive to negative. Okay, now I got to do this one, which is also a min. So at -2 and 2. Because they both change from a negative to a positive. All right, cool. So now I just got to go find those numbers. So what am I plugging in? I'm plugging in a 2 and a -2 into the original problem. Sorry, plugging in a 2 and a -2. So that's going to be a 4, and 4 minus 4 is 0, and all those powers to a 0 is a 0. So he has a min of 0 at 2 and -2, because when I square them, I get the same thing. At 2, when I plug in a 2, no. Ooh, I wrote that wrong. I hope y'all caught that. I hope y'all are sitting there saying, Miss Patterson, you have written this wrong. The max is here at 0, not at 2 or -2. That's my bad. That's on me. Sorry. So I need to plug in a 0. 0 squared is 0. That's going to be a -4 to the 2/3. Square it. That's a 16. So this is the cube root of 16. And you don't have to go in there and pull an 8 out and make it 2 cube root of 2. This is calculus. You don't have to do that at all. Okay, there you go. All right, here we go. So number 8, pause it. Go for it. Whole thing. Unpause me if you need me. I know that he has an asymptote at x equals 5. So I'm just stating that. Like he has issues at x equals 5. Derivative. Low d high minus high d low over low low. Clean it up. X minus 5 minus x, that would just be a -5, right? Yes. Okay. So now I need to look at where the derivative equals 0 and where the derivative does not exist. If I take the derivative and set it equal to 0,
and I multiply both sides by what's in the bottom, all my x's go away. So I get no solutions from him. None. So it gives me no critical values. However, does not exist. Yes, absolutely. I have crap on the bottom, and the crap on the bottom cannot be 0. So x cannot be a 5. So that is my critical value. And that goes right along with that. So that makes me feel good. So I only have one number on my number line. I'm going to plug in a 0 because that's a nice round number, and I'm going to plug in a 6. So, ooh, maybe I won't plug in a 0 because that makes it a 0 on top, and I'm looking for sign changes. Let's plug in a 4. Okay, so positive on the top, 4 minus 5 would be negative on the bottom, so that's a negative. And 6 on the top would be positive, and 6 minus 5 on the bottom would be positive, so that's a positive. No, I've just done something terribly wrong. Hold on. Plug a 4. Oh, that's right. Hold on one second. All right. So I figured out what I was doing. I was plugging the 4 and the 6 into h of x. Silly, silly me. It says f prime right beside it. Let's fix this. Now, you shouldn't have to erase all that. It's hard for me to erase little bitty stuff. This is f prime. This was f. I was taking 4 and 6 and plugging it into here. I need to plug it into f prime or h prime, whatever. All right, so I'm going to go here. So the top is going to be negative no matter what. 4 minus 5, whatever this is, it's getting squared, so the bottom's going to be positive. Top's always going to be negative, bottom's always going to be positive. That means he's negative and he's negative, which means we're decreasing and decreasing, which means h of x has no local or relative, either way you want to say it, extrema. But you have to have your because h prime of x is constantly, I did not spell that right, negative. Or you could say h prime of x sign never changes. Or you could say h prime of x is less than 0. But I feel like you need to say it's less than 0 for all x's in its domain. So I like the constantly, I knew I had an extra t in there, constantly negative. Because it's just saying that it's negative for its entire life. That way it's not going to have a relative extrema. And if you graph it, he does this. We know he has an asymptote at 5. He does like this, and then he does that, I think, something like that. So you can see it's decreasing. That's why the derivative is negative for the whole life of this sucker, and he'll never have a max or a min. All right. Last one. Whew. Okay, now this one's throwing back a little bit. Find the intervals of increasing and decreasing and find the x-coordinates, so yay, we don't have to go find the y-coordinates, of the relative extrema. Okay, pause me and go. I'm going to go ahead and acknowledge that he has an asymptote at x equals 2. So now let me find g prime. And this asymptote should come up in the when I talk about the derivative and where it does not exist. So if the function doesn't exist at 2, then the derivative is not going to exist. So this is extra. This is just me, again, acknowledging the elephant in the room. But it's going to come up when I do my derivative equal to 0 and derivative does not exist. Okay, low d high minus high d low over low, low. Oh, let's see. 2x squared minus 4x minus x squared plus 3. X squared minus 4x plus 3 over x minus 2 squared. G prime of x equals 0. Okay, so I feel like we've done this enough now to where you know that you can just take the top and set it equal to 0 because the bottom's going to go away. Okay, so I have those two, but where g of x does not exist is going to be the denominator at x equals 2. All right, here I go. A 1, a 3, and a 2. 1, 2, 3. Oh, crap, I got to plug in decimals. Okay, it's all good. Here's my derivative. Not going to make the same mistake twice. There's g prime, there's g. I'm going to take, let me change colors. I'm going to take a 0. I'm going to take a 1.5. And I'm going to take a 2.5. And I'm going to think of this top as those two factors. So I'm going to look at my derivative like this. Because it's easier for me to figure out the signs. So if I plug in a 0, I'm going to be negative times a negative over negative squared positive. So that's positive. 1.5 negative 1.5 minus 1 positive. My bottom's always going to be positive because it gets squared. That's a negative. 2.5. Oh, negative, positive. Bottom's always positive. So negative. And again, that makes sense because that's an asymptote at 2. It should not have a max or a min. And then, oh, I didn't pick somebody over here. Let's pick a nice round number, 4. Let's see, 4, positive, positive, positive. So increasing, decreasing, decreasing, increasing. All right. So it said find the intervals increasing, decreasing. Okay, so I. No pronouns. Who's our guy? G. G of x increases from negative infinity to 1 and from 3 to infinity because f prime of x is greater than 0. G of x decreases from 1 to 2 and 2 to 3. Don't make that one big group because your function doesn't exist at 2, so you have to hop over it because f prime of x is less than 0. All right, so there's that part. Now let's do double I. Find the x coordinates of the relative extrema. Okay, well, at least I don't have to find the y's. So this is going to be a max. So no pronouns. G of x has a relative max at x equals 1 because f prime G prime changes from positive to negative. G of x has relative min at x equals 3 because G prime changes from negative to positive. Whew. All right, there it is. Good times. This is like a beautiful blend of derivatives and crunchy math, little trig, some unit circle, I mean some good like absolute value graphs, like some good crunchy math, but then with the calculus application. And then being able to justify, being able to write the calculus, which is all the word stuff. Pay attention to your details and let me know if you have any questions.